All right, we will just start our webinar today. Welcome everyone. Thank you for joining us on a Wednesday morning. Hope all of you have grabbed your breakfast as well as morning coffee and is starting the day fresh and energetic with us. So before our webinar starts, allow me to do a quick introduction. I'm Bernadette from DKSH Singapore, and I will be your moderator for today. And together with me is Xingyue. She's the application specialist at NanoFCM. She's an expert in various isolation strategies as well as characterization techniques of EVs and viruses. And at present, she's engaged in the development of EVs isolation methods. So just some housekeeping matters to share. First, we have gotten our live poll up on the right, and it will continue to run until the end of our session today. So do take a few moments to answer our questions so we get a sense of the live community with us. Let us know what are some of your samples, what are some of the samples that you're working on, whether it's EVs or viruses or exosomes, liposomes, or other nanomaterials. And if you do not see the poll section, I want you to kind of direct to the bottom right of your screen where you see an icon with 3 dots. So you just simply click on it and the right panel will appear with the poll. So yeah, we do want to take every opportunity to connect with all of you. So we do appreciate if you could take some time to complete our poll. Also, let me introduce other interactive features, which is our Q&A. And again, if you don't see it, you can find at the bottom icon with 3 dots that says Q&A. So we will leave some time nearing the end of the presentation for a live Q&A. So if any of you have questions for Xingyue along the way, feel free to send them across. And also you will be receiving the slides as well as the recording of this webinar via email after today. So you don't really have to worry about missing out on any slides. So you just have to pay attention to our presenter and take this opportunity to ask her any questions that you have. If you have any other further inquiries, feel free to contact me after today's webinar. So this is today's agenda. Xingyue is going to do an introduction of the Nano-flow cytometry technology, as well as share with you guys how the Flow NanoAnalyzer can be used to characterize the size, concentration, as well as biochemical properties of biomolecules at the single nanoparticle level. Xingyue will then move on to focus on applications as well as case studies. And then we will conclude our session with a Q&A. So without further ado, I will now pass my time over to Xingyue. Xingyue, I'll just pass you the presenter rights, and then you can share your screen from there. Yeah, Xingyue, you can try to share your screen now. Yes, I can see your slides. All right, Xingyue, I'm just going to unmute you. All right. Yep, we can hear you loud and clear.
Can you hear me?
Yes.
Okay. Welcome everyone. I'm Xingyue Yuan, application scientist for NanoFCM. And today I will be introducing you to a Nano-flow cytometry platform, a high-sensitive, comprehensive analysis platform for nanoparticles. One of the things I will point out is that both the extracellular vesicles, the research field, and plenty of other nanoparticles need such a comprehensive detection machine. To our company, NanoFCM aims to bring a reliable and quantitative measurement to all asked questions in nanoscale, provide a very unique opportunity to have a good view of the full picture of various nanoparticles. So we do a lot of work with the flow results, and we got the nanoparticles and nanomedicine and a few mistakes of mitochondria and stuff. There is no doubt to support the emergence of new classes of diagnostics and therapeutics. So today's focus will cover the three topics: the overview of current techniques and how nano-flow cytometry detects nanoparticles, and some application sharing. First of all is the techniques overview. Before talking to our comprehensive nano-analysis platform, I want to start with the individual of different techniques for nanoparticles analysis. Currently, there are some characterization techniques are commonly used for single particles analysis, including TEM or cryo-TEM, NTA, TRPS, and conventional flow cytometry. They all have their own advantage and disadvantage. The leading one is TEM or cryo-TEM, which can give more accurate measurements of particle size. However, is a time-consuming technique, needing a high-level spatial info, and the sample preparation is rigorous, low throughput, and the concentration and the fluorescence of particles cannot be measured. The other two of the most commonly used instruments for characterization are NTA and TRPS. So here's like NTA, nanoparticle tracking analysis, is to track and analyze the Brownian motion of each particle in the suspense, and then calculate the hydrodynamic diameter and concentration is criticized for its accuracy. It's more suitable for samples with uniform particles. Samples like EVs, which have large heterogeneity, will lead large deviation between the dimension results and the actual results. So there's like TRPS, resistive pulse sensing, very sensitive and is a more correct approach for measuring particle size and concentration as the particle pass through the pore. There is the thing that those three techniques mainly focus on physical characteristics of particles, like size and concentration. For NTA and TRPS, not only can they not reveal about the physical and biochemical properties of nanoparticles at the same time, and they can hardly detect particles smaller than 17 nanometers. In addition, we know that flow cytometry is the premier tool for single-cell multiparameter analysis with many advantages, such as quantitative, multiparameter, fast speed and high throughput, high statistical accuracy, and so on. Unfortunately, the sensitivity of flow cytometry is far behind the requirements for nanoparticles. Based on the recent report for light scatter-based EV measurements by flow cytometry, only a couple of highly sensitive flow cytometry enabled detection of EVs of 300 to 600 nanometer in size. Due to the limitation of detection sensitivity, it's difficult to achieve the detection of particle size less than 200 nanometer and fluorescence sensitivity less than 200 FITC molecular sample. But what about the true size of EVs and other nanoparticles? Actually, whether the EVs or virus or other nanoparticles, most of them are smaller than 200 nanometers. As we know, the particle size of electrons is in the range from 30 to 115 nanometers, and virus are small in size between 20 and 200 nanometers. Besides, there are a lot of lipid nanomedicines as small as 100 nanometers. In a word, conventional streaming is really not able to meet our single particle characterization requirements for nanoparticles. Even though flow cytometry can detect EVs larger than 300 nanometers, no problem. But we need to be aware that conventional flow cytometry does miss the majority population of EVs. That is the case. So I fully agree with what Dr. Phillips said. The extracellular physical analysis by flow cytometry can only see the iceberg. So we really need some submarine that can dive down to the sea to be able to see the full picture of EV. So, either way, there are still many potential problems with those current methods. What is the future research really need? There is gonna have a combination of those parameters with the high sensitive, high resolution, high throughput, and ease of use. So we can detail understanding the complex EVs and other bio-nanoparticles. That's also the reason we choose nano-FCM for our research. The nano-FCM is based on the conventional light scattering flow cytometry, retain its excellent performance and push down their sensitivity and resolution limits of the conventional flow cytometry. But how does the instrument actually achieve it? So what we have here is a restitution of how different our nano-FCM and how to achieve this new level of resolution and sensitivity. For any nano-FCM, the sample flow is hydrogen-connected, focused on a very fine stream pass through the detection area with the sheet flow, and then it shows individual particle measurements. Transient time of nanoparticles passing the laser is extended to milliseconds. This is a longer dwell time to protect the detection by the detectors. And finally, the nano-FCM use the high-sensitive single photon counting modules process detection. So the nano-FCM do really reduce the background and enhance the signal. Another thing is that the light scattering signal and the fluorescence signal can be detected simultaneously, and the multiparameter quantitative characterization can be realized. So real-time information of particle size and concentration can be obtained by direct measurement of scattered light from individual nanoparticles. On this slide, we can see every burst traces of blue represents one nanoparticle passing through the detection area, and the peak height can represent the light scattering intensity. Through concurrent fluorescence detection, the phenotyping information such as surface proteins of nanoparticles can be got as well. similar to the scatter line. Every burst traces of green represents the fluorescence signal. And on the right, we can see the dot plots, which show the data of the fluorescence signal versus scatter light signal. On this slide, we can see the detection limits of our nano-FCM. The left is sensitivity. Nano-FCM did a great performance by pushing the scattering detection limit of flow cytometry down to the 30 nanometer of EVs. Is able to detect low refractive index, such as a single silicon nanoparticle with size down to 24 nanometer, and for gold nanometer for gold nanoparticles, because the high refractive index, we can detect 7 nanometer gold. And the detection limit for fluorescence is about 3 Alexa flow molecules or single PE molecule. It's worth mentioning that the detection of a single PE molecular signal means that the low copy proteins on the surface of nanoparticles can also be detected. And we can see the right is the resolution. For multi-mixture samples, our instrument takes only 2 to 3 minutes to obtain the average result of cryo-TEM. We can see the distribution profile obtained by nano-FCM. This fully resembles that of cryo-TEM. Not only light scattering intensity, but also the fluorescence intensity. Our nano-FCM can achieve high resolution. So here is the biological samples. EVs from HCT15, which is human colorectal cancer cell. We can see the particle size distribution for the EVs. Firstly, we can see that the median particle size measured by cryo-TEM is 15.5 nanometers. And the medium size measured by nano-FCM is 50 nanometers, which is very close to the result of cryo-TEM. It is proved that nano-FCM can more accurately reflect the properties of biological samples in particle size measurements. Moreover, we can see the distribution profile obtained by nano-FCM. This fully resembles that of cryo-TEM. And the cryo-TEM took 2 to 3 days to count samples, more than 1,000 particles to get this distribution. While the numbers of samples detected by nano-FCM can reach 10,000, is more statistically. And then for the EV samples, the peak position and the peak shape obtained by nano-FCM and the cryo-TEM, they are very comparable. But for the result obtained by TEM, we can see the peak area is too wide. And on the right of the slide, we can see the medium particle size is significantly different between nano-FCM and NTA. That's because our nano-FCM use the silicon particles as a standard, which have a refractive index closer to the biological sample. Therefore, nano-FCM is a better choice for the characterization of single particles or mixed samples, which have 3 detectors of one side scatter detector plus two fluorescence detectors, combining light scattering and fluorescence detection. High-resolution distribution of particle size and biochemical properties can be acquired simultaneously in 1 to 2 minutes. If the analysis is only for particle size and particle concentration, we can directly measure the samples by scattering light detection of our instrument. In terms of biochemical properties, mainly for functional macromolecules such as lipids, proteins, and nucleic acids, need to analyze with the help of fluorescence signal corresponding fluorescence probes, such as some protein antibodies, nucleosides, or lipid dyes. You can decide according to your own needs. There is a workflow for EV detection by our nano-FCM. We can detect the samples from biofluids or conventional medium. You can isolate EVs by your own methods, and like I was saying, if you want to analyze the size and concentration, you can choose the label-free analysis. If you want to know some biochemical properties, you can choose the fluorescence analysis. And then we choose the silicon nanoparticles as a standard because they have a comparable refractive index to the bio-nanoparticles. You can use the antibody tagging to identify subpopulations. There is an example about EVs labeling. We can see the dot plot can be clearly divided into two groups, the FITC positive population and the FITC negative population. And then you can do dual staining as well. And you can get the double positive population by getting. For the characterization results, our instrument can also directly generate detailed data analysis reports. In addition to concentration analysis reports, there are individual particle size reports and the comprehensive analysis reports can be selected. The type of report can be determined according to the needs of yours. No good instrument can be separated from practical applications. Know about the performance of nano-FCM is one thing. Another thing is how can we use the nano-FCM for our future research. Next, I will specifically introduce some application and cases, which can also give you a brief reference for the future research direction. Up to now, there are many practical application cases of our nano-FCM. I will select some representative cases to share with you since time is limited. First section is about the cases of EVs. Because the lack of particularly suitable methods of EV isolation, the choice in this area is very important for research. So I'm gonna share you a study, comprehensive evaluation of isolation methods of EVs. This article published in JEV. 3 typical samples of cell supernanos, urine and plasma was selected as the sources of EVs, and isolation methods such as ultracentrifugation, precipitation, gas exclusion plus ultrafiltration were compared. Different indicators were used for comparison, including yield, purity, particle concentration, and protein concentration. It can be seen that the purity of EVs is the lowest by precipitation. And in this research, our nano-FCM mainly measured the particle size, concentration, and the protein profiling during the different isolation stages. The second section, I will share you 3 studies on EV-based drug delivery platform. One is from the Kodiak. The EV-based medicine candidate of Kodiak has entered clinical phase 1. Nano-FCM plays a key role. Delivery of cargo tethered to the EV surface or packaged inside the lumen are key strategies for generating therapeutic EVs. Firstly, they selected a list of potential scaffold proteins, which can become drug carriers, and then they need to identify the ideal scaffold from those. They used many methods and equipment throughout the process. There is no one can tell them whether the interesting protein is effectively packaged into the EV in the single particles until they used our nano-FCM. By nano-FCM, they identified 2 scaffold proteins, PTGFR and BSP1, which can load of a wide range of molecules. PTGFR is expressed on the surface of EVs, while BSAP1 is expressed in the lumen of EVs. Now they have used those 2 scaffolds to build their own EV-based drug candidate Win platform. 3 drug candidates were constructed. Another similar case is AstraZeneca. They are using a strategy similar to Kodiak's, also selecting their corresponding proteins by our platform. Finally, about EV-based drug delivery, there is another case to treat metastatic peritoneal carcinoma. Thermosensitive liposomes were fused with genetically engineered EVs. The resulting EVs liposomes hybrid nanoparticles bear thermosensitive engines inside and express CD47 on the surface, while CD47 on EVs has proven to release the signal "don't eat me." And so the hybrid nanoparticles not only can avoid immune clearance of body, but also can inhibit the development of tumors. In this case, nano-FCM was used to determine the fusion efficiency. On the other hand, expression level of CD147 on the hybrid nanoparticles was measured by nano-FCM, standing with the FITC CD147 antibody. On this slide is a case about a study on colorectal cancer. The author of this paper did a study on the early cancer diagnosis with our nano-FCM, hoping to build a liquid biopsy method for early cancer. Nano-FCM provides a sensitive and rapid platform for surface protein profiling and size of individual EVs, which could greatly aid the understanding of EV medium, intercellular communication, and the development of advanced diagnosis and therapeutic strategies. Here, they apply the nano-FCM to analyze the expression of CD147 on EVs isolated from HCT15, HCT116, and EVs from a normal colon fibroblast as a blank. The CD147 was labeled by PE. We can see the dot plots of fluorescence were less scattering intensity for EVs isolated from different cell lines, whereas less than 10% of EV population was CD positive for the blank. This percentage increased to nearly 15% for cancer cells, which means that CD marker is potential utility in cancer diagnosis. It should be pointed out that the results measured by our nano-FCM resemble that of Western blot, while the sample amount of our instrument is 1% of the Western blot, and measurement by nano-FCM, you can get much more information like the size range. By the comprehensive analysis of nano-FCM, CD147 positive EVs might be useful in the early diagnosis and the prognosis of cancer. In this case, it's a case from the Mayo Clinic in the United States. Because the time is limited, I will not introduce the research background. In a word, our nano-FCM measured the size changes of EV under different conditions. The results showed that the increase of frequency of electrical stimulation, the diameter of EVs gradually increased. This sample also shows that our nano-FCM can track the effect of regulatory factors of EV. Next slide will introduce the cases of virus. Viral particles have many natural characteristics that can be applied to nanobiology and nanomedicine. The physical and chemical properties of virus, such as size, concentration, biochemical components, as well as the packaging efficiency of functional molecules would cause direct effect to their application. Conventional plaque titer and TCID15 are the most classical approaches for concentration measurement of effective activity. However, they quantify only those which cause visible cell damage, that include the virus without infectivity. Therefore, a virus analysis method which can quickly and reliably detect, quantify, and characterize virus particles with single particle sensitivity is highly needed. Here, the nano-FCM is introduced, which can direct detect MC2 virus with particle size as low as 27 nanometer by light scattering. Accurate distinguish between intact virus and virus-like particles is important for the effective quantification of the virus data. To examine the feasibility of using nano-FCM to differentiate intact virus, empty capsid, and naked viral genome in a mixture. Those three compositions were analyzed separately after staining with Ceto-82. The result we can see from the slide. For the empty capsid, only the light scattering signal was detected, and the peak height was much lower than that of the intact virus. This can be attributed to the low refractive index of the empty capsid compared to that of the intact virus, which thus gathers laser light. The main steps of producing virus-based vaccines include virus inoculation, harvest, purification, and emulsification. In addition to characterizing the complete virus, nano-FCM can also used to the quality control of viral vaccine. Clearly, the virus concentration measured by TCID15 was 3 orders of magnitude lower than the determined by nano-FCM. And in particular, physical virus titer measured by nano-FCM agreed much better than the titer quantitated by qPCR. Lentivirus is the most widely used vector in CAR T cell therapy. A complete CAR T cell process includes the preparation of lentivirus vectors and the production of CAR T cell products. Comprehensive characterization of lentiviruses is crucial to the successful construction of CAR T. The size distribution of lentivirus is measured through the direct light scattering, membrane permeable nucleoside nucleic acid dye is used to label the RNA, while the VSVG protein is specifically recognized by fluorescence tagged antibody. We can see the results from our nano-FCM. We think that a particle with both RNA signal and VSVG signal is identified as an effective lentivirus vector. So our nano-FCM multiparameter comprehensive characterization platform for lentivirus is crucial important. In addition to the direct measurement of lentivirus concentration and purity, the nano-FCM can be applied to all the steps of lentivirus manufacturing, from R&D, production, purification, and quality control. We can do a lot of work about the lentivirus. Next slide, I will introduce the cases of nanomedicine. In the development of nanomedicine, nanoparticles are used as carrier to deliver payload, such as therapeutic agents, thus the simultaneous detection of both nanoparticles and their cargoes is important. There is another long story about dogs carrying liposomes, and I will not go into it here for the sake of time. I'm going to focus on how our instruments play a role in this story. The characterization of particle size distribution of dogs' liposomes usually requires cryo-TEM and complex 3D reconstruction technology, which typically take 2 to 3 days. And the obtained particle size distribution is not statistically representative. On the other hand, the efficiency of individual particles loaded with dogs could not be measured. Here, nano-FCM was used for rapid and simultaneous detection of scatter light and fluorescence signals of individual lipstone particles. With the help of particle size standards, comprehensive characterization of dogs' lipstones, including size distribution, particle concentration, and dogs encapsulation efficiency was achieved in only 2 to 3 minutes. In addition, the fluorescence intensity is also quantitative, which relates to the number of drag molecules. The fluorescence intensity can further reveal the correlation between the particle size and the content of stocks loaded in each particle. And then the lipid nanoparticles loading siRNA are currently the most extensive clinical validated means of enabling RNA interference. However, it is challenging to measure the process particles count and the fraction of loaded particles. In this study, nano-FCM is used for quantitative multiparameter characterization of siRNA-loaded lipid nanoparticles. Upon fluorescence staining with Cyto82, we can get the fraction of siRNA loading. The concentration of lipid nanoparticles can be quickly obtained by signal particle counting, which can be used for concentration determination and copy number measurement of siRNA per lipid nanometers. The same method is used for the mRNA-loaded liposomes. Using the light scattering intensity, we can measure the particle size and concentration. With the help of fluorescence probe, we can measure the loading efficiency. And we can see the result in the slide. All in all, there are many directions that can be applied, but the detection methods are always the same. In addition to the cases I have described above, there are many excellent studies using our instruments. Our instrument has been promoted to 15 regions and countries. I'm looking forward to the opportunity to cooperate with you. And up to now, our nano-FCM is applied to many other articles, publications. Thank you for listening.
Thank you so much, Xingyue. It's now time for the Q&A. We do have some questions from the floor already, but we'll just give all of you some time to key in your questions if you do have. So audience, do keep your questions coming and we will get Xingyue to answer some of our questions. So Xingyue, the first question that we have is, can EVs be measured in an environment of high background like plasma? I will just key in the chat the question so you can see. I repeat again. So the question goes, can EVs be measured in an environment of high background like plasma?
If you choose the suitable isolation, we can measure the EVs from plasma.
All right, thank you. The next question goes, can we change the flow rate of the system?
Wait a moment.
No worries. Meanwhile, audience, if you haven't completed the poll is still running and it's on your right panel. If you do not see the poll section on the right, you may click the widget with 3 dots on the bottom right of your screen that says panel options. So at the bottom right of your screen, if you hover over the 3 dots, you will see something that's called panel options. And if you click on it, you will be prompted polling. So you just simply click on it and you would see the polls on our right side. So if you haven't completed the poll, we would really appreciate if you could take some time to, share with us some of your challenges so we know how we can help you moving forward. Yeah, Singret, so the question...
Yeah. All right. We can change the flow rate of the system. All right. It is depend on the shift flow.
All right. We have the last question with us. Do you have to calibrate the instrument to examine particle size ranges? So I'll repeat again. The question goes, do you have to calibrate the instrument to examine particle size ranges?
Oh, sorry.
Sorry, do you mind if I add some comment?
Yeah, go ahead, Ling.
Yeah, we have two series of standard beads. The first one is for small EVs, and the size range is from about 60 to 150 nanometer. And we have a larger size range for larger EVs, and the size is in the range of 150 to about 800 nanometers. Yeah, we do calibrate the size range using our standard beads.
All right. Thank you so much. Oh, we actually have a couple more questions coming in. We actually have 3 more. So, audience, do be patient. We still have a couple of questions left. So it goes, what instrument requirements must one consider before analyzing EVs with flow cytometry?
Sorry, I don't think I followed the question.
I'll just key in the question for you in the chat. So it goes, what instrument requirements must one consider before analyzing EVs with flow cytometry? So I think the question is asking more about the instrument requirement.
I think the first one is the sensitivity of the instrument. So we can use the standard beads to evaluate the sensitivity of your flow cytometer. So you do have an expectation of your size range of your EV samples. So if your flow cytometry is able to cover the size range of your particles, then this instrument is able to test your samples. I'm not sure if I had made myself clear.
All right, thank you so much, Ling. Do let us know if the question has been answered. So, Ling, the next question goes, what is the smallest size of the particles that the equipment can detect? So basically the size range, what is the smallest size that can be detected?
Yeah, it depends. So if you are looking at a very heterogeneous samples like EVs, then we need to make sure the larger particles do not saturate our detectors. So the smallest size is 40 nanometer. So if you are looking at very monodispersed particles, like silicon nanoparticles or very monodispersed bacteriophages, then we can go down to less than 30 nanometer.
All right, thank you so much, Ling. We have a couple more questions regarding the equipment itself. So the next one goes, what is the configuration of your equipment?
Oh, so so there are two configurations. The first one is the single laser. It's equipped with one side scatter and fluorescent channels. And the second one is the dual laser. So the difference between the single laser and dual laser is the number of lasers. So the number of channels are the same. So you have more options to of the dyes for the dual laser system.
All right, the next one regarding the equipment is the equipment capable for normal cell lines compared with conventional flow cytometer?
Unfortunately not, because nano FCM is focusing on small particles for nanoparticles, and the cells are too large for us.
All right, thank you so much, Ling. We have the last question here. It's a long one. I have already copied the question in the chat, so if you would need to refer, so the question goes, does the percentage show in the dot plot represent the absolute percentage of particles that show positive detection?
This is the percentage is for the sample only, and we all know there are some particles in the background, see in your buffer or in the sheet flow. So we need to deduct the blank particles from the ratio. So from the very appearance, it looks like it is the absolute percentage, but we need to do some calculations to correct the exact positive ratio.
All right, thank you so much, Ling. Do let us know if the question has been answered. And that marks the end of our webinar. Thank you so much for joining us, and it's 11 a.m. On the dot. So thank you so much for joining us. If you do have other questions for either Xingyue, Ling, or myself, you may drop the question, you may email your question to bernadette.lim@dksh.com, and we will get back to you as soon as possible. So thank you so much for joining, and I hope you have a great day ahead. Thank you, and see you. Thank you so much, Ling and Xingyue.
Thank you.
Thank you. Thank you.
Bye.
Thank
Bye.
you.
See you. See you.
See you.